All right, so ladies and gentlemen, we're going to start off by looking at this function. F of x is equal to x to the third minus 8 over x minus 2. Ready? Here we go. Poof, there it is. I know. What? There it is. In fact, I'm going to zoom this out just a little bit. There it is. Now, taking a look at that function. What type of a function is that? It's a parabola, which means which family of functions does it fall in? Probably a quadratic. We're looking at that. Now, the reason why we're looking at that, just looking at the form of this, why would this appear as a quadratic even though this is clearly not a quadratic? There we go. Man, last period was like, Yeah, if we factor out the top one. Now, I'm going to admit, this is a difference of cubes. I recognize that it's a difference of cubes. If you asked me to just go ahead and factor that right now, I'd tell you, hey, that's cute. Real quick, go to my computer, go on to Purple Math, and figure out what that formula was supposed to be, because I can't remember it for the life of me. Anybody else in that boat? Yeah, okay, see, look at that. We're honest in this room. All right, but we could, because we can see that there is definitely a quadratic here, it's clear that this denominator had to have factored out. In fact, if we do factor it out, it happens to look a lot like that function. My question for you, is there a difference besides color between f of x and h of x? And if there is, what is the difference? It's like being in a like crazy club. All right, sorry.
X minus 2 would cancel out, creating a hole.
Bingo. There's one spot in this graph where there is a problem, and it is this x minus 2 in the denominator is going to wind up giving you a divide by 0, which we should all know from, like, I don't know when you learned when you can't divide by 0, but it was a while ago. You know, dividing by 0 is like the big no-no. You are not allowed to divide by 0. In fact, if I focus in on this point, I'm going to... Now, what messes some people up is that if we look at this graphically, where is it? Boom, there it is. This is 212. It doesn't matter how far I zoom into this. You know, here's 212. Why is it that the hole doesn't actually exist? Like, why is it that there is no graphical hole? Yeah, it's a single point out of the infinite number of points coming into this one spot. One of them is the hole. Now, obviously, if we were graphing this, and if I asked you to graph it, I wouldn't, you wouldn't just graph right through it and be like, yeah, come on, you should have known there's a hole there. You would show it, but the computer doesn't know that. It doesn't have a way to do it. It wants to graph as best it can. So there's a hole there. So we know that at 2, we are going to wind up with a hole. That if I substitute in a 2 into f of x, the denominator goes to 0, we say 2 does not exist. And graphically, what we did by zooming in is we recognized that that red function was approaching a y value. If we look back at the graph, we can see that at x is equal to 2, our y is turning into, for those of you in the back, you can't probably see it, but it turns into a 12. Now, are there other ways to do that? One of the ways we can analyze these problems is by using our calculator. All right, how many of you remember doing that and it was really annoying with the table because, you had to fill in the table and you had to type in 1.75 in for x for both of the x's, and then you did the same thing, you had to type in 1.9 in for the x? Remember I told you I was going to show you some cool things with the calculator? All right, number 1. Here we go. So I go to my calculator, go to y equals. First off, if you don't know how to put in the fraction, it's really nifty, and I'll show it to you later. But you can put a fraction into the calculator. And one of the cool things about this is that this F1, F2, F3, F4, they actually have submenus. The submenu for trace F4 happens to be a bunch of y variables. So if I select y1, the equation I just typed in, and I go, what is the first one, 1.75? Instead of typing in 1.75 into all the x's and then hitting enter, it does function notation for you. It just put in 1.75 for both of the x's for you immediately, knew that was the equation, and did it for you. We're going to do that a lot. because we're not allowed to round problems until the very end, so we're going to get some really nasty looking decimals that are going to be like 15 numbers long. And we're going to be using that store function a lot in the calculator. And then we're going to be using this plug it in stuff. So y1 is going to be this. Pretty cool. We like that. So if I wanted to, I could say, just copy that over and change 1.75 into 1.9. There it is. By the way, go ahead and write down those numbers in the table, because you got a table. Might as well fill it in, right? If I want to know 1.99, just type it into my calculator. Of course, we already know what value we should be approaching. We saw that graphically. But if you can see, we start off 10.562, 11.41, 11.94. Clearly, that increase is becoming smaller and smaller. If I take it out to 1.999, well, we seem to be having an issue. We seem to be hitting a particular number. At least it seems that way to me. And if I check on the other side, of course, I could actually, just so you can see it, I'm going to do it a slightly different way. I'm going to go y1. I'm just going to retype it. Oh. I'm going to retype it. Just so you can see, you can do this with a problem that gives you a divide by 0. So it will give you the error if you need it. What do they have? 2.001? Suddenly I'm just barely on the other side of 12. We typically take these to 3 decimal points. In the calculator, I would probably, well, we'll talk about where to take the decimal points. Right now, just record 3. But we will learn eventually that we have to, just depending on the problem, use a longer decimal. 2.1, that's easy. 12.61, this is good. And then, of course, because it's fun to put in something ridiculous, because that's a useful piece of data. So we can see that we can come up with this table of data. And when you look at that, and when I read the question, if I read this table from the left side, you can see that the numbers started smaller and ascended and looked like as we moved closer and closer to 2, the values got closer to 12, right? If we approach from the right side, we saw the same thing. What we would say then is that the limit of f of x as x approaches 2 is 12, or again, writing it like this, none of this should be new. This line right here, though, is going to be one of the most important lines for you. Have any of you ever been guilty of using the phrase, I know I didn't write exactly what was supposed to be there, but it was really close. It was like close enough, so come on, you should take that. Anybody ever try that one with their teachers? Yeah. All right. I will tell you, on May 14th, and you take that test, and they go to grade your paper and you put an equal sign when you were supposed to put an approximate sign, you've lost all the credit for that problem. If you were to write something down and you were in a hurry and you want to write this specific limit statement and you write that, you would not get credit for that work. Because I didn't tell you what I'm taking the limit of. I'm just taking the limit of empty white space. Apparently the limit as x approaches 2 of empty white space is always 12. Now we know. But we have to be careful with our notation. I am going to be incredibly stringent about that. All right? Some of the beauty of mathematics is that our notation is very clean and concise. There is no ambiguity. It's supposed to be very obvious. So we've got to be careful. Just to give you an example, another example of what I'm thinking of is, let's say I knew that f of x, we're going to make it something easy, was x plus 3. And I wanted to know what is f of, 2 plus 4. Easy question, right? So what would we do? Well, what do I need to do? I need to find out what is f of 2 first, right? So f of 2 is 2 plus 3. Which is 5, right? So if I want to know what f of 2 plus 4 is, what do I do? Okay, see, you're doing it right. Most people go, well, I just need to add 4 to this. That's wrong. Why is that wrong? Is f of 2 2 plus 3? Yes. Is 2 plus 3 equal to 5 plus 4? No. How should I have written it? I should have done this, and then maybe over here done 5 plus 4 is 9. See what I'm getting at? And we're picky about this, so you have to be aware of it. So I really just need to get a stamp that says notation error, so that because I write that down so many times, I think I go through at least 5 red pens with just that phrase. I should have the official notation error pen. That'd be pretty cool just to see how far I actually destroy it. Other things we need to know how to do. We need to know how to write the following limits. We need to understand how to write the limit of f of x as it approaches x, as x approaches some value c from the left side. How do we write that? Hopefully you remember that. So what are we taking? A limit of f of x as x approaches c. But I want to approach c from the left. How do I write? Negative. Where's the negative go? Top right. Boom. Yeah. Just to give you a heads up for the sake of just being honest here, on some of your papers you may see something that looks like that. That was just a technology situation where I couldn't get that negative sign to be a superscript, so it's just kind of, I had to do what I had to do with the technology. But I will try to do my best to make sure. Most of these I think are right, so that's nice. And if I wanted to approach from the right, we would say the limit as x approaches c from the right of f of x. Good old review stuff. If I were to graph this particular function, I would expect you to graph it more like this, where I would obviously show the whole. We would say that that limit does not exist, or the limit is 12, but f of 2 itself does not exist. So real fast, let's just do a quick reminder. What is the answer to A? Limit as x approaches 1 from the left of f of x. It does exist, actually. It is not 2. It's 1. So how do we do this? So one of the things about limits that we have to remember is when I'm looking at a problem, you have to understand there's a difference between a limit and an f function. All right? In this problem, it says the limit as x approaches 1 from the left. So I look, here's my f, right? I want to go towards the 1 from the left-hand side. So as I go towards the 1 from the left-hand side and I get really, 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 really close to 1, what number am I getting close to? 1. On B, limit as x approaches 1 from the right-hand side of f of x, we would look at f of x and go, well, what does this graph approach from the right side? 2. So what is the limit as x approaches 1 of f of x? Ah, man. Nicely done. It is does not exist. I don't like to have the equal sign there because does not exist. It's kind of hard to equal something that does not exist. Just saying. But, you know, if there's an equal sign, we can deal with that. Why does it not exist? Who said that? Boom, Douglas. Do you like Douglas or Doug? He probably doesn't want Doug because then suddenly everybody's like, let's do the Dougie, yo. I'm sorry, Douglas. How many times have you heard that joke? Nah, I'm a jerk. Okay, so what Douglas said, though, is that this limit does not exist because the two one-dimensional limits are not the same. He said that the left, basically, that the left limit was not equal to the right limit. And they're two different numbers. I will tell you, I have seen some really creative answers. For instance, one of the answers that I've seen on occasion, people put that. I understand where you got that. Cool part about limits, there's only ever one output, so we do not, at least with the real number problems that we'll deal with, so we do not have to worry about there being multiple solutions to this. What about f of 1? I heard it. Did you say that, Timothy? I thought, there you go. 2. Boom. Why is it 2? Yeah, it's a solid circle as opposed to being open. So it's pretty straightforward. Nothing crazy going on there. All stuff that we've seen before. So far, so good. Page 1. Easy. You got this. You got this. So we just talked about one of 3 reasons that a limit will not exist. Douglas stated reason number 1, if the left side and the right side don't equal the same thing, we don't have a limit. 2 other reasons why we are going to not have a limit. The first one I'm going to state is that the function increases or decreases without bound. What the heck are you talking about, increase or decrease without bound? Well, we actually have a word for that. We say that that has an asymptote. We need to make sure that we understand that asymptotes are important. And we're going to talk about that because what we need to understand here with asymptotes is that you have how many of you have written infinity on your paper before? It's nothing crazy, right? You've been doing a lot of infinity since Algebra 1, right? But have you ever really considered what infinity is? What is infinity? Is it a number? And a lot of us want to treat it like it's a number because we use it in math. And in math, we always use numbers. And then we got used to using letters. And then we realized the letters were numbers. So we're like, everything's a number. Infinity is not. Infinity is an idea that says that that number continues to grow. We are continually getting larger. Or negative infinity, we are continually getting smaller. So if I tell you that the limit as x approaches c of f of x is infinity, I am telling you that that number never stops increasing. How do you say that it is this thing? This is a statement of equivalence, but this doesn't have a value. It just keeps growing. So when we talk about infinity, we need to get used to that because we're going to deal with infinity a lot. There's nothing worse than when I see people put infinity divided by infinity, infinity over infinity equals 1. Which you should hopefully know is not true from pre-calculus. That's one of the 2 indeterminate forms that we use a lot. 0 over 0, infinity over infinity. They're both bad. So we have that. The second one I want to introduce you to is when the function oscillates. This is when my people who have PTSD from physics are going, ah, and my people who are excited about physics are like, yeah! So for some reason, oscillation just scares people. I don't know. It reminds them of physics. I apologize for those of you who didn't like physics. That was my minor in college, so that's totally like my jam. So, and calculus kind of exists because of physics, so I'm partial to physics. An example of oscillation is actually my g of x function here. This is the sine of 1 over x. It doesn't look very interesting right here. So let's zoom in on it and see what it actually does. I lost it. I found it. So as you can see, the function kind of curves off, goes to 0 from the negative side. It goes to 0 from the positive side here. But then it starts to go through its periods. But then it starts to become very dense right here. Why is that so dense right here? Yeah, the period is decreasing. It's just going through faster and faster and faster and faster. In fact, as we start to zoom in on this, we can see that period a little bit better, how it keeps shrinking. If I zoom in even more, this gets really like, whoa. Yeah, I was going to say, whoa. I can zoom in really close. This is a difference of 1/100th. There you go. You can zoom into 5/1000ths. You can see that this period just keeps getting closer until you hit this super hyperdense region. As we get closer to 0, it just keeps bouncing up and down and up and down, faster and faster, never actually reaching a value. Part of that is that when this x approaches 0, that x is getting smaller, which means 1 over x is doing what? As the denominator decreases, the whole fraction, rational, should get bigger. And if you don't believe me, I have proof of that. Hey, always have proof. Never, hey, do what I tell you to do. There you go. There's my proof. Graphical proof. It's not really a proof. But as that x is getting smaller and getting closer to 0, you can see that this is getting really large, really stinking fast, right? So it should make sense that as this keeps increasing and its rate of change keeps increasing, that oscillation just keeps bouncing it. So in those situations, we're going to see that we are going to have a does not exist limit. So let's take a look at another one. A, limit as x approaches 2 of f from the left side of f of x. What are you going to say? Negative infinity. Love it. Perfect. That would be the best answer that we could put. There is a secondary answer that could exist, and I want to make people aware of it because on a multiple choice, it could actually come up either of these options. Remember that negative infinity is not actually a value, so does that limit actually exist? It doesn't. It just says this graph keeps going down. Limit as x approaches 2 from the right side. Positive infinity or D&Es? Yes, on a free response question in either of these situations, you would have gotten credit for either of them. The better answer is negative infinity or positive infinity because having the directionality is just a little bit more information, but D&E is not incorrect. But when we look at C, what should the answer be? Has to be D&E. Why? Yeah, I've got two different infinities that I'm dealing with. Now, flip one side over, suddenly we have two possible answers. If I flip the left up, now the answer becomes infinity or D&E. So we need to be aware. I would prefer you to put the infinities or the negative infinities, but I need you to also understand that D&E is a viable solution. On a multiple choice, if I put D&E, you're not going to see the infinity. F of 2 does not exist. Sweet. I knew someone was going to do it. All right, other things we're going to look at real fast is end behavior. We're going to get into end behavior a lot more in about a day or two. But when we take a look at this, we do look at x's going to negative infinity and positive infinity. So when I say the limit as x approaches negative infinity of f of x for this left side function, what we're really saying is that the x going to negative infinity means that our x's are just getting smaller. So as the x's are decreasing and moving to the left, what is our function doing? Increasing. So what does it increase to? Infinity. X approaches positive infinity. See, that goes to negative infinity. What about the right side graph? 4. We can see. I put the dots up there so you can see the asymptote. Makes life a little bit easier. Bottom of function, -2. A little bit of review, nothing crazy, right? So there we go, folks. We got ourselves started. All right. So there are the notes. And